Okay, so today we're going to be doing the lecture for the fourth lab. So that's going to be the column. And, okay. So yeah, we're going to be doing that lecture today. But before we get started on that, we're going to cover a few things about the memos. So memo 1, I'm almost done with it. Usually I like to grade those within a week and get them back to you within that week. Obviously, that's not been the case for the first memo. That's taken like forever and a day. So I'll get that probably done by tomorrow. So I just need to grade all of the abstracts now, and that's it. So again, yeah, that'll be up by tomorrow. Sorry it's taken so long, but the first memo, I want to give everyone a lot of feedback on that. So it takes just a really, really long time, especially when I have 3 sections to grade. So yeah, so from here on out, I'll still give feedback on every memo, but I'm thinking the individual feedback will be a little less so I can save on time, because what happens is I'm typing out like the same thing on a lot of the memos, and that just takes a lot of unnecessary time. So I'll give some feedback on each memo in the future, but what I'll do is kind of aggregate a lot of the things that a lot of people, I don't know, have like the same kind of mistake or there's something to improve on, and I'll make a little list and then we'll talk about it. So that's what I did for your second memo. You know, when you guys turn that in on the submission page, I had like some bullet points going over some areas, I don't know, for improvement in relation to the first memo. So hopefully everyone saw that. I think I sent out an email about that though. But I want to go over that before we start today's lecture. Okay. So we're going to do that. So the first thing is that all figures and tables need a caption with a number. So I don't know. I'd say about half of you didn't do this. So if you look at the memo template, which you can access by going to modules and then go to resources, and then there's the memo template. Okay, so if you have a figure in a table, you need to have a caption that's numbered. So what I mean by that is the caption here, in this case it's for table 1. Same thing if you have figures, it should be like figure 1, figure 2, etc. So you gotta have that numbered caption, and then you need a description in your caption. Okay, so that's the first thing. And I think Microsoft Word, and I'm sure like Google Docs, they hopefully have something similar, but Word has a caption function for you. So when you input a figure, it should automatically update the number of that caption or of the figure. Okay, second thing is the references section. So most of you did have a references section, which is good. But remember that your references, you need an in-text citation. Okay, so here's an example here. So this is in like my pretend results section. Okay, here's an in-text citation, and then down here we have the references section. I don't really care what format you use. There's like, what is it called, like MLA, right? Or APA. Or you can do IEEE, which is the kind of engineering standard, and that's what you see here. So you need to have that as well. If you're typing out equations, use the equation editor. So as an example for the sample calcs, and here, you know, I use something else. I use something called LaTeX. I don't use Word, but if you're using Microsoft Word, use the equation editor so everything looks nice and pretty. I don't want to see, like, if you're having a superscript or something, you have that little caret. I don't want to see that. So make sure that you use the equation editor whenever you're typing in equations. Okay. If you present a figure or table in the results section, you need to have commentary on it. So that would be what I call interpretations. Okay, so we go to the results section. And all of this stuff, by the way, in this memo template, it's in the syllabus. but this memo template is just a little bit more in depth. So if you have a figure or a table, you need interpretations. Okay, so that's explaining to the reader what your data, whether it's graphs or tables, what it tells us. So, for the first memo, what I would have recommended is you would have all of your figures, put the tables in there, and then you would discuss them. So, what material was strongest, which one is most ductile. If you're talking about ductility, you would mention the percent reduction of area or the strain at fracture, and you touch on if it was expected or not. So if it was an unusual kind of thing, you should talk about that. I think in this lab, there was one group, you guys know who you are. There was a little dip in your curve, right? And so because there's a little dip in that curve near the UTS, you should talk about that in the results section. And I think most of you didn't. So that's something you should talk about, because that was an unusual thing that happened. Okay, so there's that. Let's see what else we got. Presenting numeric results is often better as a table. So if you didn't use a table when you were presenting your results for like the UTS, elastic modulus, percent error, all of that stuff, I didn't mark you down for that, but oftentimes it is better to use the table for that. So I just thought I would mention it. And then in the discussion section, you need to kind of tie it together to real world applications. Okay, so let's go back here, discussion section. So this is when you would, talk about it in the beginning here. You're going to begin this section by restating what the experiment was. So for the first experiment, it was a tension test to determine the material properties and discuss its relevance to engineering. So explain why this tensile test is important. And when you tie it into like a real world application, talk about something where tension is important. So just as an example, there was a lot of people that talked about bridges, right? And that's fine, but you should be specific for what part of a bridge has to deal with tension. So that'd be like the tension cables that you have, right? Not the bridge itself. That's more of like a bending stress. But make sure that whatever experiment we have, that you're being specific for that kind of test. So memo 1 and 2, tension test. Memo 3, bending stress. So you want to focus on that. Your third memo is due next week. So when you talk about this in your third memo, make sure that for whatever real world example that you're talking, or you're being specific for bending stress. And then there's one more thing. Yeah, so my feedback is once you go to your assignment, once I publish the grades, you should be able to click on your assignment, and I think it's on like the top right, you click on submission details, and it should take you to a page that looks similar to this. So what I've done is I made a rubric, so you can check out everything there. It's just what is in the deliverables and the syllabus, that kind of breakdown. So you can check out the rubric. I have a lot of comments in there, but I also have comments on your actual PDF. So I really want to make sure that all of you check the comments on the PDF too, because on some of them I have a lot of comments. Not that it means you did bad or anything, but sometimes I use the PDF function, to have comments on there more than I use the rubric. It just kind of depends. So make sure you check both of them. So it should be on this kind of page here. Check out the rubric, check out the PDF comments, and yeah, and then that should help you out for your future memos. Okay, and so that's it for that. Again, the grades will be up probably by tomorrow. That's my goal. I just gotta grade the abstract. Okay. Alright, so that's it for that. And before we get started on the actual lecture for the notes, we're going to go over it in VKS. So again, this experiment is the column. So first experiment and second experiment, that was a tension test, right? And then the third experiment was a bending stress test. And this experiment is going to be on compressive stress. So we're going to have all of these columns here. I think there's 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got these various columns here. They're kind of hollow. They're aluminum 6061 T6. And we're going to get all of these columns and apply a compressive load to them. And we're going to see when they fail and how they fail. So what we'll see is the short columns, they're going to fail mostly from kind of crushing. And as we get to these long columns up here, they're going to fail from stability failure. So they're going to buckle. They're going to deflect outwards quite a lot. And for the 3 different setups that we have in the lab, they're each going to have different end supports. So here we have a fixed pin setup. So a fixed support up top and a pin support on bottom. And we also have pin fix. That's a different variety or variation of it, but fixed pin or pin fix, that'll be the same kind of thing. And then we also have fix fix and then pin pin. So for us, we only have 3 stations, so we're going to have pin pin, fix fix, and fix pin. And basically, you know, we're going to be in groups of 3 this time. I'll talk about that next week. But you know, your group, you're gonna have one setup, whether it's pin pin, fix fix, or fix pin. You're gonna do the experiment only for that setup, but you're gonna in your memo, you're gonna use all 3 data sets. So you're gonna have a data set for pin pin, for pin fix, and fix fix. So you're gonna be using data from other groups. All right. This dial gauge here, it's to measure deflection. We're probably not going to do that because measuring the deflection, that outward horizontal deflection, is a really big pain in the ass with really shitty results. If you're looking at these short columns, it's really hard to find where this kind of plane of deflection is occurring. So it might occur where we have this dial gauge here, but it might be like coming out of the screen or into the screen, or to the right at some kind of weird angle. It's really hard to find that initial plane of deflection for these short columns. And because of that, the data is just really, really bad. So, and it also takes a really long time too. So we're probably not going to do this. What we'll do instead is just continue to apply a compressive load, and then it's going to fail at some point. So we're concerned with that load right before it fails, and then also the length of the column. Alright, and let's see, there's one more picture that's useful. So you see we got a short column here, and here is a long column after it's already failed. So this is probably the 12-inch column, and you can see that because it's a long column, it's going to deflect outwards quite a lot. Alright, so that's a little preview of what it's going to look like. So now we will do the lecture notes. Okay, so just a little heads up, this lecture is going to be longer than last time. It might take about an hour. So, I don't know. Just to let you know. Compared to the second lecture, that one is really fast, right, on the strain gauge. But this one will be kind of one of the longer ones. Alright, so the columns. So before we get started, just to kind of have a little understanding of stability, let's talk about the first 2 experiments that we had. So those were tension tests. And when you have a tension test, that force, that axial force that we have in tension, it's being kind of aligned along the longitudinal axis of that rod. So when we're pulling this apart, it's stable. But when we have a compressive load, those two compressive loads, on the top and the bottom, they tend to get misaligned, whether the loads are themselves misaligned or they can get misaligned because our test specimen might not be a perfect kind of cylinder, and because of that, the loads are going to get misaligned, and when that happens, at some point, our column is going to deflect. Okay, so because it's inherently unstable because of these loads being misaligned, at some point we're going to have those loads get misaligned, and then we're going to have failure. We're going to have some deflection. Okay, so again, when we have a tension test, the forces, they align along the longitudinal axis, so it's statically stable. Okay, but for a compression test, it tends to not be statically stable because, again, those loads, they get misaligned. Okay, so when those forces get misaligned, then buckling occurs. I might say buckling, or I might say deflection. So buckling or horizontal deflection, same kind of thing. But I might say either or. Okay, so a column is going to be just a straight prismatic bar that's subjected to compressive axial load. So, we got a rod and we're applying compressive loads on it along that longitudinal axis. Okay, and then buckling is going to be defined as this sudden, very large deformation when there's very little increase in load. So as we apply a compressive load to the rod, we're going to be applying that load at a constant rate. Well, that's going to be the goal. We want to apply at a constant rate. And at some point, even though there's little to no increase in this load, there's going to be a very large increase in this horizontal deflection. So you can kind of think of it, it's like it's similar to in the first two tests for the tension test when there's yielding. So when there was yielding, we were applying this load at the same constant rate, very gradual, but all of a sudden there was this very large increase in our deformation when there was little to no increase in the load. So same kind of thing with this test. There's going to be a very little increase in load, but all of a sudden there's going to be this very large increase in the horizontal deflection. So we're going to have buckling that's going to occur. Okay, so I'm going to add on there that buckling occurs only for long columns. And we'll talk about this a bit later on for what's a long column, what's a short column, and what's an intermediate column. So this would be an example of a long column. So I'm going to apply a compressive stress to it. And so there's a very little load right now. And then all of a sudden, it's going to deflect, outwards. Even though I'm just gradually increasing that load, at some point it's going to deflect quite a lot. Okay, so buckling, it occurs for long columns. And also to note, when there's buckling that occurs, that's stability failure. So it's not material failure, so it's not like it's failing because of yield stress or something like that. It's failing from stability failure. And again, that's because those compressive loads, they get misaligned, and at some point there's going to be that very large increase in the deflection. Okay, so we're going to briefly talk about equilibrium, and that's going to be important for something that's going to be called the neutral equilibrium, which is going to occur when we reach our critical load, which is going to be really important for this experiment. We're going to convert that critical load to critical stress, and that's going to be what we end up plotting. So we'll talk about that after equilibrium. But we just want to go over the cases of a stable system, unstable system, and then kind of in this limbo phase in between stable and unstable neutral equilibrium. Okay, obviously this is not a column, right? But it's just to make a point here. So in our stable system, if we have a ball here in the center, and we are going to move it up to the left or to the right, eventually it's going to come right back down in the very middle. So this is kind of like, we're in the elastic region. We can deform our system, in this case move our ball to the left or to the right. And once we release the load or release the ball, it's going to come back to its very original position. So we are in a stable system. I know this seems pretty like elementary stuff and kind of a little abstract and weird, but it's just to get to the point of the neutral equilibrium that we're going to talk about. So next thing is an unstable system. So if we got our ball here in the center and we move it to the left or to the right, well, obviously it's going to fall off of this little semicircle that we have, and it's never going to go back to the original position. So this is kind of like plastic deformation. At some point, we're going to apply a load. In this case, we're moving the ball to the left or to the right. And once we do that, it's never going to return back to its original position. So this is an unstable system. This would also be like when we have that buckling that occurs on our long columns. At that point, once it buckles, we can't go back to the original position. It's unstable at that point. My iPad seems a bit laggy today, going from the iPad to my computer, so sorry if it's kind of, sporadic or jumpy. So next thing is the neutral equilibrium. So for this, we're in between stable and unstable. Yeah, I don't know, kind of weird. Okay, so for this, if we have our ball in the center, And if we move it to the left or to the right, we're going to move where it's located, right? But it's not going to fall off. We can move it to the left and it'll be at the left position, but we can kind of move it back if we want. Really, the point is that we're in between stable and unstable. We're neither stable or unstable. So I can move it to the left, but it's not falling off of this like make-believe surface. So in this case, it's kind of like we can have some deflection, and we could move it back. We haven't gone into this plastic kind of deformation region. It's a weird kind of limbo stage. We're in between stable and unstable. But once we get past this point, we're going to be unstable. So again, I think these kind of drawings are a little weird. I mostly did them because they're in the textbook. But I think it's easier to actually think about the experiment itself. So we're going to be applying compressive loads on our columns, and we're going to get to this this critical load, it's called. And at that point, we're in what's called neutral equilibrium. But once we get past that point, then we are in this unstable system when we fail. So the column is going to fail at that point, and it won't be able to take any more load. Alright, so that's the main important thing. Okay, so our critical load, I'm going to call that P of CR. So P, the load, CR, critical. Okay, critical load. So if our load P is less than the critical load, then we're in a stable system. So we can kind of recover all of that deformation if we have any. Right, and then if our load P is greater than the critical load, that means we are in an unstable system. So we have that buckling that occurred, or if it's a short column, it crushed and we can't recover any of that kind of deflection or crushing that's occurred. Basically just deformation. Okay, and then if the load is equal to the critical load, that's when we're at this point of neutral equilibrium, kind of in that limbo phase. We're in between being stable and unstable. So we're teetering on the edge. And once we get right past that, anything after this load, then we are unstable and the column has failed at that point. So again, once we actually make our graphs, we're going to take this critical load, we're going to convert that to stress, and that'll be what we graph. So that's indicating that that was the last load or stress that the column could withstand. And anything right after that, it failed. And so what you'll see is once we're doing the slab, we're going to apply load, and you'll see that all of a sudden it can't take any more load, and that's when you've reached this critical load. Okay, so there is an equation for this, and this equation is, it's only going to be applicable for a long column, which we still need to define what's a short column, what's a intermediate, and what's a long column, because right now that's really vague. So we still need to define that, but there is an equation for long columns. It's called the Euler buckling load equation, and so we can use it for long columns to find or estimate when this critical load is going to take place. Alright, so here it is. This is the critical load, again, for long columns only. So we can estimate when this critical load is going to take place by having this equation, pi squared multiplied by the elastic modulus multiplied by the moment of inertia, all divided by the length squared. Okay, so that's going to be our theoretical equation to estimate for a long column when we're going to reach our critical load. So if we look at this equation, we can basically make our system more stable. You can kind of think of it that way by increasing the stiffness, right? So if I choose a different material that is more stiff, has a higher elastic modulus, I can increase our critical load. So we're going to need a higher load until we reach this critical load, which is implying that we're going to fail. So if you want to make sure that your column fails at a higher stress, then you can choose a different material. So maybe instead of, I don't know, aluminum, you choose some kind of steel. You can do that. Or a different way, you can keep the same material, but you can just change the geometry. So if we increase the moment of inertia, same kind of thing, we can increase then that critical load. So it's going to fail at a higher load. And even more importantly is the length. So the length, since it's raised to the power of 2, it has a bigger impact than either the elastic modulus or the moment of inertia. So if we increase the length, or let's actually say, let's decrease the length, then we can increase the critical load again. And that makes kind of sense, intuitively. If you have a short column and you're trying to compress it, it's not going to fail. It will fail, but you need to have a very large force on that for it to fail. But if you have a really long column like this, it's really easy for it to buckle. So, kind of like a hint, this is a question that I like to have on the final once we get to there, which will be how to increase the stability of a column. So you can do that by changing the material choice, so you have a stiffer material, or change the geometry, so you want to increase the moment of inertia, or decrease the length of the column. You can make it a more stable column, meaning that it takes a higher load for it to reach the critical load. Okay, so we have our critical load, and just like labs 1 and 2, we want to take that load and convert it to stress. So we're just going to take the load and divide it by the cross-sectional area of our column. Okay, so I'm going to call that sigma of CR for critical stress. Okay, so we have our load divided by the cross-sectional area. Okay, so there we go, right? Just load divided by cross-sectional area. That's going to give us our stress. But we're actually going to rewrite this now into a different format. So let's do that, and then I'll explain it. So we have pi squared times the elastic modulus, and this will now all be divided by L divided by K squared. Okay, so L divided by K is something called the slenderness ratio. So we'll talk about that in a second. It's a kind of geometric property. And K, that is the radius of gyration, which is also a geometric property. And basically, we just rewrote this equation. So K is I divided by A, or really K squared is I divided by A. Okay, so again, k squared is I divided by a, the moment of inertia divided by the cross-sectional area. So it's a geometric property. And then L divided by k, that is, again, a geometric property because we have the length, we have the moment of inertia, and the area. And that's called the slenderness ratio. And we're going to use that to basically define if we have a short column, intermediate, or a long column. So this is our method, so we're not being vague, what's a short column or a long column, right? It's not just going to be the actual length of the column, it has to be more than that. And in this case, it's again going to be the length divided by the moment of inertia divided by the area. Okay, so I should also make a note again that this equation for critical stress, because it was derived from this Euler buckling load equation, it's only applicable for a long column. Alright, so the slenderness ratio again is L divided by K. Okay, I might call the slenderness ratio SR because way less syllables, right? Okay, so that's what we have, and again, it's a method to define if we have a short column, intermediate, or long column. Okay, so for a short column, basically what we're going to do is just plug in for L divided by K, and we'll solve for that. And if it's less than 49.67, it's going to be a short column. Alright, so that's all we got to do. So basically, we'll define the length in MATLAB and we'll solve for K. And then we'll be able to sort out if we have a short column, intermediate, or long column. So for intermediate, that's going to be when L divided by K is in between 49.67 and 63. Okay, and then a long column is when L divided by K is simply just greater than 63. Alright, so there we go. So we have our metrics now. So far for what we have here, we can find the critical stress for a long column, and that's it so far, right? We haven't defined how to find the critical stress for an intermediate column or a short column. And we're going to add on to the complexity right now by talking about those different end supports that we have. So this equation here for critical stress, that's actually built in with the assumption that we have a column with pin-pin end supports. But we could have fixed pin and we could have fixed too. And that's going to change how the critical stress is, or what the value actually is. So we're going to complicate it a bit more right now, but it's all going to tie together kind of nicely in the end. Okay, so again, our theory so far was assuming that we had a pin-pin and support, but we can have fix-fix or fix-pin. So to deal with that, we're going to use the concept of effective length. So effective length is going to be defined as the equivalent length for a column that's pin-pin. So if we have a fix-fix end support column, we're going to use effective length to say, okay, for that fix column, the effective length for a pin column is going to be this. So we have an equation for that. So for a fix column, it's going to be 0.7 times the length of that column. And for I said the wrong one. So for a fix pin column, that will be 0.7 times the length of the column. And for fix, it's 0.5 times the length of the column. So I'll write all of this out. Okay, so pin column, because our theory was derived from a pin column, the effective length for that is just going to be the length of the column. Okay, and then we'll have a fix pin column. It'll be either fix pin or pin fix, that's the same thing. Sorry, I missed a question. So, equal to 63. I know to be specific, but would it fall into long or intermediate? Yeah, actually, when I was writing this out, I was thinking about that myself. I need to double check that actually. I think if it's equal to 63, so if it's greater than or equal, I should have said, then it's a long column. But I'll double check that for when I do the data reduction video for this. And then this one up here, that should be less than or equal to. But I'll double check that. Okay, so fixed pin, that effective length is 0.7 times the length, and then we can have a fix column as well, and that effective length is going to be 0.5 times the length. I need to write out the definition as well. I know we talked about it, but I'll write out the definition for effective length. Okay, and again, effective length for fix is 0.5 times the length of that column. Okay, there we go. Alright, so any questions on this part here? Okay, so now we have the effective length. So let's go over what we can actually calculate so far. So we have our equation for critical stress here, and currently that's only for a long column. And that was built in with the assumption of a pin-pin fixed support, or sorry, a pin-pin end support setup. But now we just talked about the concept of effective length, and that's covering the different end support setups that we have. So we can use these now, and we can actually plug in the effective length and substitute that in for the length part in our equation. And now we can solve for the critical stress for a long column for all of our different end support setups. So for pin-pin, fix-pin, and fix-fix. So we're actually going to take all of the equations that we wrote so far, and we're going to substitute in the effective length for length. Okay, so all we're going to do when we see an L, we're just going to plug in LE instead. So that's our critical load, and we'll get our critical stress here. Alright, so those two equations, remember they're derived from the Euler buckling load equation. That's for long columns only, but now that we have the effective length concept, we can plug that in, and we can solve for these long columns for any end support. And then last thing here is the slenderness ratio. So that's for if we have a short column, intermediate, or long, for how we define those. Now we can define that in conjunction or adding on the effective length concept for the different end supports. Okay, and then again, we're just going to change L to L sub V for the effective length. Okay, so there we go. Now we're getting somewhere, but now we need to talk about short columns and all those different end supports, and then long column or intermediate columns with all the different end supports. Okay, so for short columns, it's kind of a crude approximation. So we don't have an equation for this, a theoretical equation. All we have really is the crude approximation that the short columns, they're going to fail by yield stress. So it's going to fail by material failure. Alright, so this is in contrast to the long columns, okay, up here. So remember, we said that long columns, they fail by stability failure, not material failure. So that's when they buckle. Our short columns, they are going to fail by material failure and not stability failure. So again, they fail by yield stress. Okay, so for the aluminum columns that we have, the critical stress, again, that's going to be equal to the yield stress, and that's 39, this is a comma, that's 39,177 psi. Okay, so that's when they're going to fail. But again, this is a kind of a crappy approximation, because, once we get to our test, we have 12 columns. It might be that we have, maybe 3 columns that are classified as a short column. So that's an increasing in length. And as we increase in length, we know that the critical load or the critical stress should be decreasing because we're increasing the length. And that's going to change, again, that the critical stress is going to go down as we increase the length of the column. But here, we're just saying that the no matter the actual physical length of the column, if it's classified as a short column, we're just saying it fails at this constant value of the yield stress. Okay, so it's kind of not great in that way. So you'll see later on, we're going to draw a theoretical curve and what your experimental curve might look like. So once we get our experimental values, you'll see that the short columns, they actually do vary for that critical stress, but theoretically we're saying that they fail at the yield stress. Also going to add on there that when they fail by yielding, they crush, just like we talked about before. So they don't really deflect outwards much at all. They do a little bit, but it's not very much. So we're going to say that they fail by yielding and that they kind of just crush down. They just smush down, kind of like a soda can. Alright, so intermediate columns. Obviously in between short and long. So for this, there is actually a formula. It's not a theoretical formula, but it's a formula that was derived from tests. So it's an empirical formula. And this is given to us from the manufacturer. So there's some constants that we have, and the manufacturer basically supplies those constants. Right, so the equation for this is B minus D. So those are the constants that are given to us from the manufacturer. And then we multiply that by the slenderness ratio. Okay, so for us, B is going to be equal to 38,300. And then D is going to be equal to 202. Right? And then, of course, because we're looking at critical stress, the units in the end are going to be in units of psi. Alright, so there we go. So now we have the ability to map out basically the critical stress for any length of column. So whether it's short, intermediate, or long, we have methods to approximate them. So short column, we're going to say it's going to fail by yielding. Okay. And then for intermediate columns, it's going to fail using this formula here. And it's going to be a combination of crushing and buckling. So, if we're closer to a short column, it's going to be mostly crushing. But if we're closer to a long column, it's going to be mostly buckling. Okay, so it's kind of a mix. And again, we have this for all of the different end supports here, because we have the concept of effective length. And then for the long columns, we have our Euler buckling load equation converted to critical stress, and we can solve for that for any end support as well. Okay, so once we conduct the lab for your memo, you're going to make a graph. And this graph is going to be the critical stress on the y-axis. Okay, and then on the x-axis, we have the slenderness ratio. Okay, and in this black curve is the theoretical curve that we're going to plot. And this is going to have three different sections, because as we increase with the slenderness ratio, we're going from short columns to long columns. Okay, so for the first part, we're going to have these short columns. And remember that these fail by the yield stress. So here we have a constant value for the critical stress. Even though we're increasing in our slenderness ratio a little bit here, we're still saying that theoretically it's going to fail at this constant value, which is the yield stress. So again, it's not a great approximation. Okay, the next point in the graph, or next section, is going to be the intermediate section, intermediate columns. Okay, and then these, we're going to use our empirical formula for that. Okay, and then we have our long columns, which we have the Euler buckling load equation converted to critical stress. We're going to use that. Okay, and there we go. So this, again, it's our theoretical curve. So we're going to make a plot for this. And we're also going to have a plot overlaid on the same graph for our experimental values. So we have 12 columns. That means we should have 12 experimental points. So we're actually going to show the points on this graph, and then we'll connect them. And then we're going to compare our theoretical curve to the experimental curve. So remember, we also have 3 different setups in the lab for those different end supports. So, in this graph here, let's just say it's pin-pin, but we're also going to have another graph for fix-fix and another for fix-pin. Okay, so in pink there, those are our 12 points. It's not going to look this kind of smooth how I kind of drew it out here. But imagine that those are the experimental values. So again, we're going to compare the theoretical curve to the experimental curve. And we'll look at the differences and see what that's like. So, usually we say that there's percent error. We're comparing the experimental values to the theoretical. And we're saying that our experiment had some error, which is, that's always going to be the case. There's always going to be experimental error of some form. But what I just kind of want to talk about is, again, this short area here. Our theoretical metric was that it's gonna fail by yield stress, but that's It's not a great approximation, again, because we're increasing the length, and because we're increasing the length of the column, it's going to fail at a lower stress here. So just something to think about, to talk about in your memo for this lab. Alright, so that's what it's going to look like. We're going to have those 3 different graphs in the memo. So also, once we do the lab and I upload the deliverables for this lab, I'll give you the equations for the moment of inertia for that kind of hollow cylinder that we have for the columns, and also the equation for the radius of gyration. Of course, you can look it up, but I'll just give it to you guys on the deliverables handout. They're simple formulas. And then we're going to plug that into MATLAB, and we'll go through the data reduction, and then you'll make your memo. Okay, and I'll state this again next week before we start the lab, but just a little preview. Usually we've had the software apply load itself, so we didn't actually have to really do anything. We just hit play, right? But for this lab, we're actually going to have to increase the load ourselves. So we're going to use the hand controller to increase the load by using the thumb wheel. And the thumb wheel, if any of you guys have used it so far, I don't think many have, but if you've used it, you know that it's really sensitive. So we got to be really careful next week once we're doing the lab to really be very, very, I guess, slow when you use the thumb wheel. Because if we're, testing a long column, those fail at really low loads. And it's really easy to use the thumb wheel and already just get a value in, like 200 pounds. And if you do that, you might have the long column fail, sooner than you meant to. So we got to be careful of that. Okay, in the short columns, once we get into the lab, we're going to be doing intervals again. So for short columns, it'll be intervals of 75 pounds. For the intermediate columns, we're going to do intervals of 50 pounds. And then for the long columns, intervals of 10 pounds. Because again, those are going to fail so much sooner than the other columns. Okay, so that's it for the theory. Before we leave though, remember that your third memo is going to be due next week. So next Friday. I'll get your grades for the first memo out probably tomorrow. I'm going to really try to get them done tomorrow. I just need to grade the abstract. So make sure you look at the feedback for that memo before you turn in your third one next week. Alright, and then next week, of course, we're doing the lab. So we'll meet at the class, although I think the class is usually locked when we get there. But if it's unlocked, we'll meet in the class, and then we'll head over to the lab. Alright, so that's it for today. The average, I don't know the average yet, because I still need to grade the abstract. So I don't know. But it seems like pretty typical to what my past labs have been like. Alright, so if you have any questions, you guys can stick around. But if not, then I'll see you guys next week, and have a good weekend.
Thank you, Professor.
Thanks, Amro. You too.
Thank you, Patrick. Have a good one.
Thanks, you too.